Good morning, everybody. And this will be the last talk for this session. So it's going to be about quite different to some of the other talks this morning on hypersonic flow. In this particular case, it's going to be past an open cavity, and I'll explain some of the terminology in the next couple of slides. And it's all using HPC. We've been using the UK's national facility. It's a machine called Archer 2. It's a Cray system, and it's about 100,000 cores on the system. So by some of the modern standards, it's not so big today. And it's using open source software as well that's freely available for people. So this is part of an ongoing study. It's not a funded project. It's something we're doing because we're interested in it. And we're sort of doing it in our spare time. And it started really looking because of how you do thermal management with hypersonics. Hypersonics has become really topical again. It's one of those topics that's been studied for quite a few years. And it's sometimes popular, sometimes not. But more recently, with the things like in the Ukraine, we've seen hypersonic missiles start to be used. So a lot of people have now got a lot of interest in understanding hypersonic work. So just a brief bit about cavities. And they're a very convenient way of keeping the flow clean around an aircraft. So typical ones by design are things like wheel wells, where you can retract the landing gear. You can use them for sensors. The euphemistic term for weapons is housing stores inside a cavity. And you can have gaps in there. If you have differential heating, you might need to have a gap somewhere. You can also happen by accident, sort of at high altitude, you might get micrometeorite sort of impacts. But you can also get manufacturing processes that lead to unwanted gaps and grooves in there. And also by damage, either through an impact, as I was saying, with micrometeorite type of thing, differential ablation. And one of the attributing factors that they believe on the Columbia disaster was one of the tiles came away, which then would create a cavity environment, which would cause a very intense and highly thermally and energetic flow around there, and that led to the disaster. So the key thing with a cavity is that it implies that the flow is going to separate, and at some point downstream it will reattach, and that alters the local flow environment that you have around that. So over the years, there's been quite a number of different ways of trying to classify cavities. But the most accepted ones today they're going to be the deep cavities, which is this image here showing where the length to depth ratio is less than 1, or they're going to be shallow cavities. And shallow have been the ones that have had the most attention. A lot of work has been done on the deep cavities, but generally around benchmarking with lid-driven cavities rather than aerodynamic features with them. So the other aspect then with cavities is you get into a situation where they're called open or closed. So this is the open cavity. The open cavity is where the boundary layer separates and reattaches. So it separates at the leading edge here, reattaches on the trailing edge. And that has implications for the flow. And if you can kind of think about blowing over a milk bottle or something like that, it generates a very strong acoustic tone. So you get lots of noise associated with these types of cavities, and you get a very unsteady flow environment. The other extreme of that is the closed cavity, and the closed cavity is where the boundary layer is reattached to the cavity floor, and you end up essentially with a forward-facing step and a backward-facing step, which have been in their own right extensively studied. There's also a hysteresis region, which is called the transitional cavity area. And this is where the flow partially attaches to the cavity floor and but it doesn't quite fully do it. If you do it experimentally and you gradually increase the gap, you will find that you get a sort of hysteresis region. And this here is for supersonic type flow, and the roughly length to depth ratio of about 10 would be the open cavity, and greater than 14, the closed cavity. But it depends on the Mach number. If you do hypersonic, the open cavity persists for around about 14. And it also depends on other factors like the boundary layer thickness at separation. So this is where we actually started looking at the problem, and it was around deep cavities. And it's to do with hypersonics having very high surface temperatures and thermal gradients. And so they want to find ways of managing these excessive temperatures. There was a really famous fluid dynamicist, Dean Chapman. In 1956, he did a theoretical analysis of a cavity flow. He had to make lots of assumptions for doing it. But based on that, he demonstrated theoretically that you got about 60% of the heat transfer rate compared to a flat plate situation. So in '69, Hunt and Howell wanted to investigate this, and they did a honeycomb structure, which looks a bit like this. And so the flow's coming in this direction. And from their experiment, they were able to show that they didn't get the 0.6, but they got about 0.7 of the flat plate. So there was some merit in doing this. The problem, certainly from our point of view, is that this is a very complicated structure to try and model and try and get any useful information from, because the honeycomb is, they look rectangular, but they're kind of squashed, so they're awkward, and it's a 3D problem. And at the time, of course, back in '69, they didn't really worry about CFD or anything like that. A year later, in using the same wind tunnel and situation, there was another experiment done by Wheating, and he simplified it down to just the single cavity here, which ran the length of the geometry, so the flow's coming in this direction. And that gave a bit easier to understand some of the flow dynamics that's going on. So, as I said, that's where we kind of started looking at the cavity properties. The area that we were looking at was the length to depth ratio of about 0.5. In the experimental setup, I haven't talked about the width of a cavity, which has an impact, but they assumed it was 2D along the center line, and the width to the depth ratio is about 2.5. So that's close. I wouldn't say it was completely 2D. So it was a Mach 6.9 hypersonic blowdown tunnel. It used a mixture of methane and air, and fortunately for us, they didn't specify in either experiment what the mixture was. And we've been looking at, we started with the 0.5, but we've also gone up to 2 now, looking at length to depth ratio 2, 1, and 0.5. The idea is that we're going to chain all of these cavities together to get closer to the honeycomb structure that was originally shown, to try and understand how that might work. So in terms of the flow, it's all laminar, zero angle of attack. But as I mentioned, there are lots of slightly unknown things, like what the wall temperatures were, and what the specific heat capacities were, and things like that. So this is what our cavity looks like. They don't even specify that distance, so you can kind of measure it and guess what it is roughly. But lots of things that we consider really important for doing a fluid dynamics study, there's not there. But we do have the temperatures, the stagnation, total temperatures and things like that. As I said, we assume the wall temperature is 294 K. We know the depth is 2 centimeters. And so in this particular case, for the open cavity, it's 4 centimeters. And we're just using air, so we're using gamma 1.4. So the two codes, this is the first code. So this is Asta. It's under development in the group. It's available on GitHub. It's a high order compact scheme. And this is some of the examples here. This is another cavity one, which is a length to depth ratio of 8, but it's also being used in a wide range of other turbulence studies of shock boundary layer interaction and more recently on combustion as well. And over here is the speed up plot, and it scales very well for what we want to do. So one of the things with hypersonics is that it can fly at really high altitudes. And so I put this in because this is quite different to continuum methods. Above a certain altitude, around about 70 kilometers, you'll start getting that the mean free path of the air will be too big, and you will start getting rarefaction effects in there. And when you get to that level, then the de facto standard for doing this is a method developed by Graham Bird in the 1960s called direct stimulation Monte Carlo. And it's basically, each particle represents a collection of gas molecules. They collide in a stochastic way, and you can do a representation of what's going on in the gas. And it's, in principle, valid for all flow regimes. So we could use it for continuum problems. And there was a paper by the developers of this code, which looked at the turbulence cascade, doing essentially a DNS, with showing that you could do it and capture that with the DSMC method. But I mean, it took an obscene amount of time to do it. But it was more of a proof of concept. So the code we're using is Sparta. It's developed at Sandia under the guidance of Michael Gallis, who's an expert in rarefied gas dynamics. It's part of the exascale computing project in the US. So under the ECP, it's been developed. So it's got GPU capability. It uses MPI. It's written in C++. And you can see some of the examples of what it does. It scales really well. And this is some results from our national facility, Archer 2. It's a very good code and probably the best in class for doing this type of work in rarefied thing. And as I said, lots of the more recent missiles that they've been using typically fly about 100 kilometers. So you can't use a continuum method at that altitude. So some results. So these are some recent results that we're doing on the open cavity, showing what the basic flow structure is going to look like with the primary vortex near the trailing edge and the secondary vortex near the leading edge. So the boundary layer comes across here. What will happen on this, as I'll show you in some of the other slides, is the flow will oscillate, right? Because the shear layer will dip in, then it gets pushed back out, and you get this continuous pumping action. And this is showing some results of the friction and Stanton number, comparing what we did originally with the length to depth ratio of 0.5, the deep cavity, and the differences between the shallow and the deep. And one of the things that we can see on the deep cavity is it's much cooler, a bit hotter at the trailing edge. So this is measuring from the top of the leading edge down along the cavity and up to the top of the trailing edge. So, but it's really quite good on that, and you get some much hotter points in the open cavity. So this is what it's some of the flow looks like. Looking at vorticity and skin friction in here, and the temperature with the heat with the wall heat flux on the monitor points, and you can see this oscillatory behavior going on here. It's really quite unsteady, whereas the deep cavity is often quite a nice, well behaved sort of flow. If we look more closely at different pressure points. So the center line here is just taken upstream of the separation point, and you can see there's no oscillations up there. And then this is taken at different points in the cavity. And you can see the oscillatory nature of the flow here, looking at how the pressure monitor is oscillating, and even more complicated on the temperature, which will depend on a lot of flow features. The period of the oscillation is about 0.1 millisecond. There's a semi-empirical expression, which you can use, and that gives the Struhl number of about 0.2. And in the theory, there was a semi-empirical formula gives about 0.19. So pretty good agreement on that. So this is a comparison now between Aster and Sparta, looking at essentially the no-slip condition. So a very, very low Knudsen number. I didn't mention the Knudsen number looks at the ratio of the mean free path to the characteristic length, in this case, the depth of the cavity. At that Knudsen number is essentially no slip, and we get very good agreement between what we're seeing with Aster and with Sparta. The cost of doing that was about 6 weeks to calculate it, right? Because it's really, really bad at doing continuum flows. It can do them, but it's very, very expensive. And it was really done just to demonstrate. But now you can see where we're running from here. This is equivalent to going up in altitude. We're changing the Knudsen number to reflect that. And you're going from what we're seeing at the continuum end, going up and very rapidly. Not much change in the Knudsen number, really, just getting into the slip regime here. And already we've got a very different flow structure going on. Kn of 100 here is essentially free molecular. That's where the molecules are only really impacting on the cavity itself and not with each other. So this is now starting to move towards the honeycomb. The eventual goal is that we'll put more baffles in here to reflect closer to what we're seeing. But we're already starting to see some interesting behavior that we need to spend more time understanding, because we've split it in two, but the second cavity gets really excited, and it's going to be some feeding mechanism coming from the first cavity. These are quite recent results, so we're still looking at this, trying to understand what what's going on. But quite an interesting result. We've also done this now with Sparta, and again we see very similar to the continuum solution over there. And as we go up, it's staying pretty much, but as soon as you get to the really high, you got two vortices being created in each one. Quite a different flow pattern emerging. So just to conclude, the work was really motivated by the experiments done by Hunt and Howell and followed on by Wheating, which was all based around investigating the theory that was developed by Chapman. The long-term goal from this is just to understand the impact of the deep cavities on thermal management, and we're slowly building up to that. All of the results are open source with the Aster code and Sparta. Both are available. Although this was primarily around the length to depth ratio of 2, which you've seen all the unsteadiness. There are other, we did do some earlier results and published those on the deeper cavity. And we've captured some of the different behavior we get at higher altitudes where the Knudsen number is important. Oscillatory behavior, it's in good agreement, particularly on sort of Struhl number prediction for the continuum. And we now need to look at other effects of trying to reflect the what was done with the honeycomb. Some uncertainty with experimental values, as I mentioned, and we'll have to look at whether the results with a width to depth ratio of 2.5 is really 2D. We might have to do the study computationally to see if there's any impact. But so that's it. So thank you.